about the bonding. Is there any question so far about the scheme or the diagram what I have explained so far? Is there any question? All right, perfect. Okay. Malak, just focus with me. Just whatever we explain, that will be simply part of the whole system, because uh, there is no piece of information which we can omit or we can simply include. It's all about a package. So whatever we explain, it's just simply part of the whole topic. Wa'ad. Okay, again Wa'ad. This is the graph again. So for everyone else, actually, just focus with me. Now, as we said, this axis is simply what we call it the distance which separated the two hydrogens. This axis, the y-axis here, it represents the energy, so the energy of the whole system. So as you can see, when the two hydrogens are far away from each other, we call this distance infinity. It means we will simply assume that the energy of the system is equal to 0. Now, when the two hydrogens started to come closer to each other, that means we will get more attraction forces, or the total attraction forces will start to increase. Why is that? As I said, for separated atom, hydrogen atom, we have nucleus attached to or attracted to one electron. Every nucleus is attracted to one electron only. Now, okay. Now, when the two hydrogens come closer to each other, the nucleus in this hydrogen started to feel the attraction of the electron in this hydrogen. The same thing applies to this hydrogen. The nucleus of this hydrogen started to feel the attraction of the electron in this nucleus. And therefore, the total attraction forces of the system will increase. As we explained in the previous lecture, when the attraction forces increases, the energy started to drop. And that's why, because of the Coulomb's law, as you can see, as the R here decreases, the energy, the drop in energy increases, because the attraction forces become more and more until we reach the maximum drop of the energy. And in this point here, we call this bond strength, which is simply the maximum drop of energy we achieve when the two atoms are bonded to each other, and the distance at which we get the maximum drop of energy, we call it the bond length. This is simply the whole graph. And by the way, this graph, always keep it in mind, because simply it explains bonding between any two atoms in chemistry. This is the simplest graph. We simply apply it to two atoms, which is in here, two hydrogens, but actually, in reality, it applies to any two atoms, any bond formed between any two atoms in chemistry. The summary of the whole issue in here is, when we make a bonding, or when bond is made, that means we have more attraction forces, and that means the energy always will drop down. You see it here. Will drop until certain the maximum drop of energy can be achieved. Now, any question? Yeah, that's actually what I see, because it's better actually if I see. All right. All right. Now in here, is there any other question about this slide? All right. Okay. Now, the importance of Lewis structures and how we draw the Lewis structures. Actually, it is very important because it can, when we draw the Lewis structure of any compound, it will simply give us an idea about how or what's going to happen or what's information we can gain from Lewis structures. In general, whenever carbon is made or has made four valence covalent bonds, that means the hybridization of this carbon is sp3. As I hope you have studied this in general chemistry. As you know, the electronic configuration of the carbon is 2s2 2p2, and therefore, as such, carbon cannot make four bonds. Because what's the requirement for any atom to make a covalent bond? Remember this. The requirement is to have half-filled orbital. Any atom cannot make a covalent bond without this requirement. This is a must. The atom must have a half-filled orbital, which means the atom has to share the bond through an orbital which contains only one electron. And therefore, just check here the valence electrons of the carbon. We have 2s2, we have 2p2. From the electronic configuration in here, in the ground state of the carbon, the total number of carbon which can make is only 2. Cannot make more than 2 as such, isn't it? Do you follow me? Why? Because simply, according to the electronic configurations, in the 2p orbitals, we have 2 electrons, and these 2 electrons, every electron is in one p orbital, and therefore the maximum number of bonds of the electronic configuration of the carbon in the ground state is to make 2 bonds. But the major knowledge, what we know as organic chemists, that carbon always made, or the number of covalent bonds which carbon can make, always 4 covalent bonds. So in order to explain this, we need to introduce طيب. It's extremely important for a question of type that why we simply mention the 2s2, why not the 1s. As I said in the previous lecture, and remember it always, all over your life, chemistry is a relationship between valence electrons. Valence electrons. Please remember this all over your life. This is chemistry. We as chemists, we do not deal with inner shell electrons. We have nothing to do with inner shell electrons. Nothing happens, nothing changed in the inner shell electrons. Chemistry is simply a relationship between valence electrons of atoms. So whenever we want to explain or to study a relationship or bonding between any 2 atoms, we only focus on the valence electrons. We don't care about the inner shell electrons. Is that clear, Taif? That's why we simply said or discussed the valence electrons of the carbon. We didn't go 4 simply inner shell electrons, because it's by default there is 2 electrons in the 1s. But this 1s has nothing to do with chemistry, has nothing to do with bonding. Is that clear, Taif? Sure. Is there any other question about it before we move forward? All right. So, as I said, for the carbon to be able to make 4 bonds, there is something needs to happen, and this is actually, first of all, 1 electron from the 2s should move to 1 orbital of the p. It is always true, Taif, for all atoms, for everything related to chemistry. Remember my words carefully. It's always, chemistry is a relationship or interaction between valence electrons. We never ever deal with inner electrons. All right. So in order for the carbon to make 4 bonds, carbon needs to make what we call it hybridization. And the hybridization in here, it's a process. It involves, first of all, movement or excitation or transfer of 1 electron from 2s to 2p. This is the first step. So in order for the carbon to make 4 bonds, as we said, carbon needs to have 4 half-filled orbitals. So to do so, as you can see, the 2s cannot be involved in bonding, because simply the 2s, the s orbital here, the 2s orbital is filled. It contains 2 electrons, so it cannot be used in the bonding. So therefore, the first step, 1 electron of the 2s must transfer from the 2s to 1 orbital of the 2p. In this case, as you can see, we will have half-filled orbital of the 2s and 3 half-filled orbitals of the 2p. And thus, we have carbon ready to make 4 valence electrons. You follow me? You follow me, guys? So far? Perfect. All right. Now, after this transfer of 1 electron from the 2s to the 2p, what's going to happen in this case actually is simply that these valence electrons, or these half-filled orbitals, they will, mix with each other, and they will form a new 4 orbitals, which we call them hybridized orbitals. So the next step, there will be mixing of the 4 atomic orbitals and forming 4 equivalent here. It's very important to remember this. Equivalent, and forming 4 equivalent molecular orbitals, which we call them sp3. Now, here, after the first step, so the hybridization is actually 2 steps. The first step is the transfer of 1 electron from the 2s to the 2p. Then the second step is the mixing of the 4 atomic orbitals and forming 4 equivalent orbitals, or molecular orbitals, which we call them, or each of them, we call it sp3. So we will have 4 sp3, 4 molecular orbitals, or hybridized orbitals, let's call them, called each of them called sp3. So that's actually the result of the hybridization, and thus simply in this case, carbon is capable of making 4 covalent bonds. And that's actually simply the formation or the explanation of the formation of methane gas. You follow me? Now, in this case here, always sp3 always will have the geometry of the orientation of the orbitals around sp3 hybridized atom is always called tetrahedral. It's extremely important, guys, to remember here, based on the Lewis structure, what will be the hybridization and what will be the geometry and what will be the bond angle around every atom. Just to remind you about this, if number of electronic groups around one atom, if it is 2, the number of electronic groups, that means the structure or the geometry of the molecular orbital in here will be linear. The hybridization will be sp, and the bond angle here will be 180. If the number of electronic groups is 3, the geometry will be triangular planar. And the hybridization will be sp2, and the bond angle between the bonds will be 120. If we have 4 electronic groups surrounding one central atom, then the geometry will be tetrahedral. And the hybridization will be sp3, and the bond angle will be 109.5 approximately. These are essential knowledge, actually, what you have learned in general chemistry 2101, but we need them, and you will need them all the time. You as chemists, you should not forget this at all. Always remember, based on the number of electronic groups around central atom, we can have an idea about the geometry of the molecule. We can have an idea about the hybridization which has been used to make this molecule, and we can have an idea about the bond angle inside the molecule. That's actually, as you can see, when the carbon here make a 4 covalent bond, that means we should expect right away that the hybridization must be sp3, and the geometry around it will be tetrahedral, and the bond angle will be 109.5. Is there any question about it, about the hybridization and the formation of the methane gas? Any question? Perfect. All right. Okay. Let's just move to the next slide. You can see the next slide in here that we have sp3 orbital on the carbon. On each carbon will simply overlap with one s orbital on 4 hydrogens. Actually, it's worth to say here, it's worth to note that all atoms, there is no exception here, all atoms try to have or to make hybridization when making bonds, and the only exception is simply hydrogen. Always remember that all atoms, regarding what this atom is, whenever they want to make bonds, they will try, or they will make bonds by hybridization, by a hybridized orbital, except hydrogen. Always hydrogen uses, which orbital hydrogen uses always in the bonding, in the overlap of the covalent bonds? Which orbital hydrogen always uses? Yes, it is 1s. There is nothing there, nothing more. That's why actually the only atom in the whole periodic table which does not need hybridization, it's simply the hydrogen. But any other atom will definitely make bonds by hybridization. Now, maybe the question is, why atoms need hybridization when they make bonding? Why do you think? Why do you think in principle atoms needs hybridization when they make bonding? Any suggestion? Okay, Jawahir, to be stable, but why? Why to Sheikha to be stable? True, but why? Why making, or when the atom makes hybridization, it will be more stable, or it will be stable? Mazen, same energy? No, Mazen, the energy actually should be less. All right. Okay, let me remind you with some fundamental issue you have learned and you have done it maybe thousands of times. When you was filling electrons in the electronic configuration of atoms in the general chemistry 2101, and whenever you want to fill electrons in the second level, so in the second level we have 2s and we have 2p. Which orbital always you fill first, the 2s or the 2p? All right, perfect. That's great. That's always we do automatically. But the question is why? Why you fill, or we fill, or we have filled 2s before the 2p? Why we always do this? Which one is the less energy? Is the 2s. What does that mean, less energy? Why? Why it is less energy? Why the 2s is less energy compared to the 2p? Now, again, it's true the 2s has less energy compared to the 2p. No, Taif, no, it has nothing to do with that. Exactly, Khawla. Khawla is correct. Exactly, Sharifa. Sharifa is correct, because simply it's all about attraction forces. We said always the 2s is closer to the nucleus, and thus there is more attraction forces, and thus there is less energy, and thus it is more stable. Remember that all the time, please, because you know what, as I said before, organic chemistry is really very lovely piece of cake topic. But if you try to understand these principles, these fundamental principles, which will be repeated all over your life, whenever you study organic chemistry, whenever you study or whenever you face a question, most likely is all about energy, about attractions. So just understand the trend in here. It will enable you to understand the whole topic of organic chemistry very easy, very simply. So let me just write it down, and please always remember it. We fill 2s before 2p because 2s is less energy, and which means the same meaning, and it is closer to the nucleus. That's actually the reason why, always. So now in this case here, as you can see, this is the fundamental issue here. We always fill the 2s before the 2p, and therefore here now, in the valence electrons, whenever you have 2s and 2p, then atoms always try to simply use the 2s, or try to involve the 2s in order to have more attraction to the nucleus, and thus less energy, and thus more stability. You follow me? So the reason why all atoms use hybridization, it's simply to lower the energy of the shared orbital, or in other words, because simply the two when the atoms uses the 2s, the 2s is less energy. That means the hybridized orbital will be less and less energy, and therefore the situation will be strong, more stable, or more attraction forces. Is that clear, guys? Is there any question about it? Okay, I assume Mazen said no question, and Wa'ad said yes, it's understood, right? Perfect, perfect. Okay, but please remember this in order not to repeat it again, because as I said, this is like the foundation of organic chemistry. If you understand this, believe me, plenty of explanations and questions and so on and so forth would be very piece of cake actually, because it's all about attractions. Always, it's not just chemistry. Everything happens in life in order simply, or the driving force for every action to happen in life, it's simply to have more attraction forces. Now, let's get back to our slide in here. As you can see here in this case, when in the methane gas, the sp3 or every sp3 orbital on the carbon, remember we do have 4 sp3 orbitals. There is a rule always, number of atomic or hybridized atomic orbitals, or atomic orbitals in hybridization equals to the number of hybridized orbitals. You follow me? In other words, if an atom, it has or it used 3 orbitals for hybridization, that means it will get 3 hybridized orbitals at the end of the day. You follow me? Oh, these hybridized orbitals, we will always call them based on the number, the type of the orbital which has been used. In other words, in the carbon here for the methane gas, it has used s orbital, 1s orbital, which is the 2s, and 3 p orbitals. That's why we call it sp3. If it has used 1s orbital and 2 p orbitals, it will be then sp2. If it has used 1s and 1 p, that means it will be sp. In other words, actually, hybridization is only 3 types, either to be sp or sp2 or sp3. That's actually the generalized 3 types what atoms can make in the hybridization. So these are simply the summary of the methane gas. Now this applies actually again for ethane or for propane, for butane, for all. Okay, Jawahir asking about the D. Of course, we are talking about carbon in this case because we said before in the previous lecture that organic chemistry is simply the chemistry of carbon compounds, and therefore we are talking about carbon. Now the carbon, the valence electrons in the carbon only present in the second ground state, which means, or which contains only 2s and 2p. So the D is not there. It is not part of the hybridization. But if you are, Jawahir, dealing with, for example, metal, for example, or inorganic compounds, then definitely then you're dealing with the second or with the third energy level and less, and therefore the D here is part of the hybridization. Got it, Jawahir? Is that clear, Jawahir? Perfect. All right. As I said, when the hybridization of the methane applies to all hybridization of carbon in methane applies to all carbons in alkane, as we will see in the next chapter when we are dealing with functional groups. So this applies to all elongated carbons or saturated carbon compounds. So you can see here for the ethane gas, we will have each carbon will have sp3 hybridization. As you can see in here, this carbon here, this sp3 hybridization of the carbon will overlap with this sp3 hybridization of the other carbon, and they will form a covalent bond between them, or what we call it sigma bond. And this, each of these sp3 hybridized will overlap with one of the hydrogens to make the other 3 sigma bonds with the hydrogens. So that's why we have, for the ethane gas, we have CH3 attached to CH3. Do you follow me? Now let's simply discuss the bonding. Actually, it's not a discussion rather than a revision. You know, this is actually what you have studied, or what you're supposed to study in the General Chemistry 2101. That's actually the orbital or the bonding of an example of this type of compounds, which we call it ethylene or ethene when we deal with IUPAC nomenclature. Now, for the ethene, as you can see it in here, for the ethene, as you can see here, we do have carbon double bond carbon here. In this case, let me just use another program, maybe it's even more clear. I'll just open up in another program. Chem3322. All right. I'll just show you, just in order to show you the whole issue here. All right. As you can see, for the ethene gas here, we do have carbon attached to carbon here. Carbon bonded to double bonded to another carbon. Oops. So we have carbon double bonded to another carbon in here, and then each carbon attached to a hydrogen, as you can see. Do you see it? Can you see what I'm drawing? Can you see what I'm drawing? Perfect. Okay. All right. Perfect. Perfect. Now, this is the ethylene molecule, what we are dealing with now. As you can see here, each carbon here, you can see it very clearly that each carbon here, for example, this carbon, as you can see, it is attached to, or it is surrounded by 3 electronic groups. It is surrounded by this group, for example. This is 1 electronic group, 2 electronic group, and 3 electronic group, sorry. And 3 electronic group. Do you follow me? That means this hybrid, or this carbon, needs to have sp3 hybridization, because always the number of or a number of bonds depends on the hybridization, or both things are actually depending on each other. In other words, if an atom needs 4 covalent bonds, then it will definitely make or needs to make sp3 hybridization. If an atom needs to have 4 or 3 covalent bonds, then it will make or it will need to make sp3 hybridization, sp2s, sorry. And if it will need, or if it is surrounded by 2 electronic groups, let's, instead of writing 2 covalent bonds, let's just write 2 electronic groups. You follow me? And then if it is surrounded by 2 electronic groups, will need then definitely sp. Check here what we are dealing here, or what we wrote in here. You see, it's all about the number of electronic groups in the Lewis structure. So as you can see, for this compound, each carbon is surrounded by 3 electronic groups. You follow me? You can see here, every carbon is surrounded by 3 electronic groups, and therefore, in this case, each carbon will need 3 hybridized orbitals of the type sp2. Always s, then the rest of the number of the hybridization. In this case here, carbon is surrounded by 3 electronic groups. That means it needs 3 hybridized orbitals. The hybridized orbitals, definitely there will be s and 2 other p of the p, and therefore that's why we call it psp2. I'm sorry, I've just wrote it here wrongly. It is supposed to be, or the hybridization of the carbon here, supposed to be actually sp2, not sp3, right? Supposed to be actually sp2. Is that clear? Because the carbon is surrounded only by 3 electronic groups, right? So it's all about the number of electronic groups surrounding a carbon atom. Now, you can see this carbon here will make a bond with this carbon, or sigma bond, what we call it, sigma bond here. There will be overlap between the 2 orbitals here, sp3 with sp3, and this sp3 with s, sp3 with s, sp3 with s, and so on. Now, the remaining orbital on each carbon, there will be a p orbital in this case. And in this case here, I'm just trying to draw it again for you. Let me just use this as a p orbital. You can see there is a remaining of p orbital in this case, and that's actually the overlap of these 2 orbitals, these 2 p orbitals here, in this case here. Just going to use something to show you. Okay, this one. You see here, this overlap between the 2 p orbitals that's actually what make pi bond, what we call it the pi bond. This bond here, or this overlap, will lead to a formation of a bond which we call it pi bond. Here, this overlap, it's overlap of, the overlap of the 2 p orbitals will form a new type of covalent bond, which we call it pi bond. Pi, I don't have the sign for it now. Maybe in here, there is no sign in here. In the sign here is in this software doesn't appear. Anyway, the pi bond here, as you can see, and the overlap, let me say here, this overlap of two sp3 orbitals will form sigma bond. Do you follow me? As you can see in here. So we have two types of bonding in here. The overlap between the two carbons, between the hybridized orbitals, sp3 with sp3, and then the remaining p orbital on each carbon. You can see this overlap between the two p orbitals will form a new type of bonding, which we call it pi bond. So between the carbon double bond carbon, or between the two carbons in this compound, we do have two bonds, two types of bonds. We have one bond called sigma and one bond called pi. Now the question is, which is the ultimate question all the time, which bond is stronger and why? Sigma or pi? All right. Now, as you can see, we do have different answers for that. Some saying pi and some saying sigma. It's actually pi, well, not pi. It's pi bond. Pi, like the mathematics. Now, the question is actually, or the answer is always, sigma is a stronger bond compared to pi bond. This is always true. Why is that? Why, Mazen, sigma is always stronger and less energetic bond compared to the pi? Why, Mazen? Mazen al-Rashdi, I'm waiting your answer. The sigma is the overlap between sp3 with sp3. Fatwa. Sigma is the overlap of sp3 with sp3. So you can see here, for example, if this is sp3, it looks like this. Let me just draw it in here. For example, the carbon here. Let me just take this away. Let me take this, put it this here. And take this, make it closer. Oops. All right. Now imagine that here, I'll just take this off. Now this sigma here between the two carbons, imagine it's actually overlap, or it has been formed by the overlap of this orbital. I suppose I should make this the size from the beginning. All right, we just do it again. Oops. It's a bit, it looks like difficult, but it's actually just, anyway, it's okay. We just say, make it like this. So between the two carbons, there is here this carbon and this carbon, sp3 with sp3. That's actually here, this bond, this overlap, this is actually what we call it sp3. We just take it all, make it bigger. All right, you take it all from the beginning. I'm just going to draw it again. It's all right, it's okay. So this bond here, we will imagine it that it has been formed by the overlap of sp3 with sp3. So this overlap between the two carbons, that's actually what will make the first sigma bond between the two carbons. And then on each carbon, there will be a remaining of a p orbital here, which it will overlap with each other. So there will be here a p orbital and then a p orbital here. Do you see it here? Now, I'm just going to make it bigger a little bit for all of you to see. Can you see it? Now, can you see it? All right. Okay. All right. Perfect. 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 All right. Now you can see here the bond here between the two carbons. It's the first bond here. We call it sigma because it is the overlap of sp3 hybridized orbital with hybridized orbital. Do you follow me? Now, this orbital is not hybridized. It's just p. It's atomic orbital. This bond here belongs to a carbon, and this bond here belongs to another carbon. Now, the overlap of these two p orbitals will form what we call it sigma. So again here, it will form the pi. So therefore here you can see this overlap is here what we call it sigma bond. And this overlap, I'm just going to show you the overlap here just in like attraction forces between the two here. This overlap, the above and below, here we call it the pi here. These are actually the two overlaps, and these are simply, as you can see, the two bonds which will be formed between the two carbons. Do you follow me, guys, so far? All right. Now, always we said sigma will be stronger than pi bond. Why? Check the structure or the drawing carefully. Now, the sigma has been formed by what we call it head-to-head overlap, which means you can see here, you can imagine the center of each carbon here is the nucleus, here nucleus, here nucleus. You see, the sigma, the electrons in the sigma are located between the two nuclei, and therefore their attraction forces with the two nuclei will be very strong compared to the pi. You see, the pi is the interaction of the electrons here above the plane and below the plane. You will see, which means that the electronic density will be above the axis of the two nuclei and below the two nuclei. So always the sigma is what we call it head-to-head interaction, which is very strong interaction, while pi, we call it side-to-side interaction, which is weaker interaction, weaker overlap, and thus weaker interaction. What's happened? It's not presenting. All right. Do you see it, guys, here? Is that clear now? Why sigma always stronger compared to the pi bond? Because actually, this is fundamental, as I said, because this is the foundation and the basics of understanding organic compounds. This is, if you understand this, this will be applied to all classes of organic compounds. Always true, sigma is stronger compared to the pi, because sigma interaction is head-to-head overlap of electrons. The electronic density will be located between or in the same axis between the two nuclei, while the pi bond, which is side-to-side interaction, the electronic distance will be above the plane of the axis of the two nuclei and below the plane of the axis of the two nuclei. Is that clear, guys? Any question about it, please? If you have any question, do not hesitate. Because as I said, this is foundation, this is basics. If you understand this, you should be able to simply understand the chemistry of very complicated organic compounds. Not that much big deal, because whatever question is related to the same basic, the same foundation, what we are dealing with from the beginning. So these are extremely important. That's why I'm just explaining them slowly, easily, in order to allow you all, guys, to understand them and to digest them carefully and nicely. All right? The reason why? Because sigma is stronger than pi, because in sigma, the overlap of electrons is head to head, which means the electron density lies between the two nuclei. While in pi, the overlap is side to side, which means the electron density is above the plane, above and below the plane. As I said always, Yani, you don't need, guys, to memorize these words or these explanation perfectly. It's all about understanding. Whenever you understand it, then simply express it by your own words, whatever it is. It doesn't matter, I mean, to be exactly the same wording as if you are memorizing, because this is not science, it's not chemistry. Chemistry is just understanding. So whenever you understand the topic, just express it by your own words. Definitely would be correct. If we say that's more closer to the nucleus, the answer is right. No, it's all about attractions. The attractions will be more. Attractions in the sigma will be more, because as you can see, when the electrons between the two nuclei, the attraction is definitely is more compared when the electron is above the plane or below the plane. The name of the molecular shape is triangular planar. Triangular planar. And the bond angle in this case, it will be actually 120 between any two bonds, or in between any three atoms actually of this molecule. Is that clear? All right, perfect. Okay, so let's move to another slide. The next slide actually will be definitely then simply let's just explain, because we are using now a software called chem3322, and you will definitely use this software when you study computers and chemistry as an elective course. Now let's just move to another molecule which we call it acetylene gas, and the acetylene gas here we will have. When you draw the Lewis structure of the acetylene, you will see it's just carbon-carbon bond, carbon triple bonded with another carbon. Oops. And then we have hydrogen. So we have here carbon, and here we have carbon, then we have here hydrogen, then here we have hydrogen. This is the acetylene gas, and it has a molecular formula of, as you can see, C2H2. This is called acetylene gas. You see it. All right. Here, in this case, for the acetylene gas, as you can see, we have around each carbon, we have how many electronic groups surrounding each carbon, guys, in this Lewis structure? Exactly. So what does that mean? It means each carbon needs to make what? Hybridization of sp. Exactly, Ahmed. We need sp for each carbon. And this case here, what does that mean? It means we will have 2 sigma of each of which the carbon will use sp. You follow me? So sp, what does that mean when we have sp atom? When we have sp hybridization, it will means that the carbon used here, I will just write it here. sp means the carbon used S and 1p. So the remaining of the valence of the carbons, guys, what will be a remaining of each carbon will be then? 2p, exactly. P orbitals, 2 of them, there will be a remaining of each carbon in this case. Here, similarly now, when we form the carbon-carbon here, this is carbon, as I said, and this is carbon. Sorry, just remove this here. Now here we can imagine that the sp is simply the overlap of the orbitals like this. So this is sp with sp between the 2 carbons. And then we do have sp with the carbon here with the hydrogen here. Now then here, and then the hydrogen, as you know, it's all about S. So this will be overlap. Oops, it's too big. Let me just use, okay, I think it's all right. Just use this and make it a bit little slow, less. So there will be hydrogen here. Copy, then paste. Okay, that's actually, this is how the carbon will make bonds, guys. We said each carbon here, this is the center here. This is where I am putting the mouse here, is the center. This is the carbon. Carbon will have, each carbon will have sp hybridized orbitals. That means that will have sp and sp. sp will be used to make overlap with one carbon, and another sp will be used to make overlap with the hydrogen, as you can see here. The hydrogen here will always use the s orbital. Now, the remaining of each carbon, there will be two p orbitals. One p orbital, for example, will be perpendicular to this plane, which will be this. And this will be formed by, and this, the bond here between them will be the pi bond between the two p orbitals. Now, as you can see here, this is one of the p orbitals which is simply presenting, but we do have another p orbital. Why didn't make it as such? To make it bigger. Yes, just want to make it bigger for you. In order not to complicate the picture here, I'm not going to draw the third p orbital, but I just want you to imagine it. It's perpendicular to this plane, so it's coming toward your vision and backward your vision, and there will be another p orbital, but there will be also overlapping between this carbon and that carbon. Can you see it, guys? Can you imagine what I'm saying? So, as you can see here, this is sigma bond between the two carbons, which will be formed by the overlap of the sp hybridized orbital from this carbon, the sp hybridized orbital from the other carbon. So let's just summarize what's the type of the bonds here. Exactly, the second is not clear because, as I said, I didn't draw it. So there will be sigma formed by overlap of sp with sp, and there will be by the first by, let's say, overlap of px, and second by, which will be formed by the overlap of pz, for example. Now, if you want to see the third one, I'm just going to try to draw it for you. And the third one will be simply, because it's a three-dimensional, so you have to remember that we cannot draw it other than, for example, here it will be like this. It will be perpendicular. And it will be, in this case, you see, that's actually now, if you can see it here, this is actually the real picture of actually what you have, what you will see for this molecule. So around or between two carbons, any two carbons, there are three bonds. Now, how these three bonds, always remember that regardless of the number of the bonds between any two atoms, there is only one sigma, the rest will be pi. So if, as you can see in this molecule, we have three bonds between the two carbons, that means one of them is sigma, and the rest of them, there will be 2 pi. You can see them, the 2 pi and the 2 pi p or pi orbitals, because the p orbitals are perpendicular to each other. This is how they look like. So this is simply the acetylene gas, and this is how it looks like, the acetylene gas bonding of the molecule. The acetylene gas will be, or the shape of the acetylene gas will be linear, or the shape around the central atom of the carbon will be linear, and the bond angle will be 180, and the hybridization will be sp. It's the pi bond here, Mazen, is only 2, because Mazen, a very good question Mazen is asking. It looks like we have like the pi bond like 4 bonds. It's actually not, because every interaction above the plane and below the plane, these two, we call them 1 pi. You follow me, Mazen? You follow me? So you can see this here, this line and this line, all of them, both of them is only 1 pi. The same thing, this two, the interaction between these two loops and these two loops above the plane and below the plane, we call them pi. So the total number of pi bonds in this acetylene gas, we have 2 pi bonds and 1 sigma. Is that clear, Mazen? Any question, guys, so far? Always 1 sigma, whatever the carbon molecule we have. Muhammad, always 1 sigma between 2 atoms. There is no way to have more than 1 sigma. Do you follow me? Why, Muhammad, you think we cannot have 2 sigmas between the 2 carbons? Muhammad, I'm just asking you, and asking everyone else, but Muhammad, try to answer it. Why, in principle, it's impossible to have 2 sigma between the same 2 atoms? I'm asking the same question for everyone else. Why it is impossible to have 2 sigmas between the same 2 atoms? Logically, why it is impossible? So what, Jawahir? Okay, head to head. So what? Why not? Yani to be had a sigma and sigma. Why not? I know, but I mean, Akram, yani why not? The sigma here is over the other sigma here, and that's it. So, and this is the 2 nuclei, sigma, sigma. Why not? It is impossible. Okay, all right. Actually, none. I don't have any. None of you gave the correct answer. Let me just tell you something. Actually, again, it's principle and foundation. It's basic. I'm just telling you this. What's the driving force of any action in life? What's the driving force of any action in life, in chemistry? Why things happen in chemistry or in life? Why? To have more attractions, Ahmed. Exactly. That's actually the ultimate driving force of any action to happen, either in chemistry or in life. So, but at the same time, anything can happen to increase the attraction or to lower repulsion, because lowering repulsion is exactly like more attractions. Do you follow me? It's either which. In this case, let's go back to the question. Why it is impossible to have 2 sigma between the same 2 atoms? Because if you have the 2 sigma between the 2 atoms, that means there will be repulsive forces between the 2 sigmas. Huge repulsive forces, because they will be lining over each other, which will then definitely make it impossible. So instead of making more attractions, you will have more repulsion. So again here, impossible for the 2 sigma to happen or to occur between the same 2 atoms, because the 2 sigma will repel each others. Because the 2 sigma must be in the same axis of the 2 nuclei. That means they will be very close to each other, and therefore there will be more repulsive forces. So to make the story short, it is impossible to have, regardless of the molecule is, it is impossible for to have more than 1 sigma between the same 2 atoms. If there are more bonds, that means definitely The other bonds must be pi bonds. I hope everything is understood so far. Perfect. Okay, I just have, it's enough for today. We are done with the lecture, but I'm just going to announce a few things. First thing, starting from the next lecture, there will be attendance, which will be made by you before the start of the lecture. So there will be like 10 minutes before the start of the lecture, you have to log in into your portal and then register yourself as attendance. You will see it in the portal today, inshallah. This is the first announcement. The second announcement for the lab of this week, it will be, inshallah, the lab will be posted today. No, tomorrow actually. The lab regarding the melting pot, the first experiment. And in the same lab, it will be also announced on the Moodle when you have to, when you are supposed to submit your report of the experiment. So all things related to the lab will be uploaded today, but the video or the demonstration of the lab will be uploaded tomorrow. The third announcement actually regarding some of you before the start of the lecture or after the starting of the lecture, they are asking my permission to enter the video, while most of you, you have access directly to enter the presentation. So I don't know if some of you make a mistake, but in all cases, what I mean, I don't want to be bothered and allowing someone to enter the presentation. So I want you all directly to access the presentation. Did you get it? Some of you, they are asking permission. You supposed not to have permission. You supposed directly to click on the link which I send you for the Google Meet, and then you must have, I see. Yeah. Thank you, Bayan. I think that's actually the reason why. Because some of you may use an email rather than the email of the university, and that's could be the reason why it will send me a message asking my permission to allow you in. While if you are using the SQU email, I think it will be allowing you directly. The lab, it will not be today. It will be actually Wednesday for all of you. Okay, Raja, you will find all details actually related to the lab maximum by tomorrow. Don't worry. So the lab of this week, every details about where to get the video and where and the lab experiment itself. The lab manual, everything will be on the Moodle. So check your Moodle, please, maximum by tomorrow. Is that fine? Okay. All right, guys. Thank you very much. Wish you a very nice day for today, and inshallah see you Wednesday.